Imagine a power plant that pumps out 400 trillion watts of energy. That's our sun. This celestial dynamo, a massive sphere of scorching plasma, governs our existence and shapes the world as we know it. At the heart of our solar system, the sun is a hotbed of nuclear reactions where hydrogen atoms fuse together to create helium in a process called nuclear fusion. This fusion generates an unimaginable amount of energy, nearly 400 trillion watts to be precise. That's enough energy to power the entire world's electricity demand millions of times over every single second. But what's more fascinating is that this process has been happening for about 5 billion years. And will continue for another 5 billion years to come. So when you feel the warmth of the sunlight on your skin, you're experiencing the ripple effect of these nuclear reactions that happened millions of miles away. The sun is not just a ball of fire, but a complex and dynamic system. It's composed mainly of hydrogen and helium, with trace amounts of other elements. This composition is crucial to understanding the sun's structure and behavior. The sun's energy doesn't just provide us with light and warmth, it drives Earth's climate and sustains life. Every living organism on our planet, from the smallest microbe to the largest whale, owes its existence to the sun. It fuels photosynthesis in plants, which in turn provides food and oxygen, the very essence of life. But the sun's influence extends beyond just supporting life. Its constantly evolving magnetic field generates solar activity like sunspots, solar flares, and coronal mass ejections. These can impact Earth's magnetosphere and cause space weather events. So, our sun, a celestial dynamo, is the powerhouse of our solar system. But how does it influence our planet? The sun is not just a silent blazing ball of gas, it's a hub of intense activity. Now you might be wondering what kind of activity could possibly be happening on the sun. Well, it's not as calm as it appears from our earthly vantage point. The sun is constantly bubbling with solar activities like sunspots, solar flares, and coronal mass ejections. These are not random occurrences, but are influenced by the sun's magnetic field, which is generated by a process known as convective dynamo action. Let's break down what these solar activities are. Sunspots, for instance, are darker, cooler areas on the sun's surface caused by intense magnetic activity. They appear as dark spots because they are cooler than the surrounding areas. Then we have solar flares, which are sudden, rapid, and intense variations in brightness. They occur when magnetic energy that has built up in the solar atmosphere is suddenly released. And then there are the coronal mass ejections. These are significant releases of plasma and accompanying magnetic field from the solar corona, which is the outermost part of the sun's atmosphere. They often follow solar flares and can eject billions of tons of coronal material into space. But what's driving all these activities? It's the sun's magnetic field. This magnetic field is generated by convective dynamo action. This is a process that converts kinetic energy from fluid motion into magnetic energy. In the sun, this fluid motion is caused by the hot gas that moves from the sun's core to its surface in a convective manner. This magnetic field is constantly evolving, reshaping itself, and influencing these solar activities. It's like a celestial dynamo, churning and creating a magnetic field that drives the sun's tireless activity. So the sun's magnetic field is a catalyst for solar events. But what happens when these solar events reach Earth? Solar activity doesn't just stay confined to the sun. It can reach us here on Earth, causing what we call space weather. Picture this: the sun, our very own celestial dynamo, is constantly at work, producing an enormous amount of energy. But it's not all sunshine and rainbows. This energy can erupt from the sun in the form of solar flares and coronal mass ejections. These eruptions send massive amounts of solar particles hurtling through space. And when these particles reach Earth, they interact with our planet's magnetic field, causing space weather events. Now, what exactly are these space weather events? Well, on the brighter side, they are responsible for the breathtaking natural light shows we call auroras. You might know them as the northern or southern lights. These mesmerizing displays are the result of solar particles colliding with gases in Earth's atmosphere, causing them to glow. But it's not all spectacle and wonder. Space weather can also have more serious implications, particularly for our technology-dependent society. These solar particles can cause disruptions to satellite communications, navigation systems, and even power grids. Imagine your GPS suddenly failing during a road trip or your city experiencing an unexpected power outage. That's the potential impact of a severe space weather event. Understanding these space weather events is crucial, not just to appreciate the beautiful auroras or to prepare ourselves for potential disruptions, but to comprehend the profound influence the sun, a star millions of miles away, has on our everyday lives. It's an ongoing relationship between Earth and the sun, a dance of cosmic forces that shapes our existence. So, space weather, driven by solar activity, has a profound impact on Earth. But to fully understand this, we need to dive deeper into the sun's structure. To truly understand the sun's influence on Earth, we need to take a closer look at its structure. Peering into the heart of our sun, we find its core, the epicenter of a power production process that puts any terrestrial power plant to shame. Here, under immense pressure and temperature, hydrogen atoms fuse into helium in a process called nuclear fusion, releasing a staggering amount of energy in the process. Wrapped around the core is the radiative zone, a region where energy travels outward as electromagnetic radiation. It's a slow, random walk for the photons, taking thousands of years to journey from the core to the next layer, the convective zone. The convective zone is where things get a little topsy-turvy. The energy, now in the form of heat, rises to the sun's surface in giant bubbles of plasma, in a process not unlike boiling water. This turbulent boiling creates patterns on the sun's surface, visible as granules or solar granulation. Above the convective zone lies the photosphere, the visible surface of the sun. This is where the light generated deep within finally escapes into space. This is the layer we see when we look at the sun, but please, not directly. Above the photosphere we find the chromosphere and the corona. The chromosphere, a thin layer of gas, is where we observe the sun's dynamic features such as solar flares and filaments. And finally, the corona, the sun's outermost atmosphere, visible during total solar eclipses as a shimmering, ethereal halo. Each of these layers plays a vital role in the sun's overall function, from the energy production in the core to the spectacular solar phenomena we observe on its surface and beyond. They all contribute to the sun's influence on our planet, driving the Earth's climate and sustaining life as we know it. Understanding the sun's structure is crucial, but equally important is its composition. The sun is mainly composed of two elements, hydrogen and helium, but that's not the whole story. Dive a little deeper into the fiery furnace of the sun and you'll find it's not just a simple ball of gas. The sun is a complex, dynamic, and yes, even a diverse place when it comes to its elemental makeup. Now, it's true that hydrogen and helium are the stars of the show, making up nearly 98% of the sun's mass. Hydrogen, the lightest and most abundant element in the universe, makes up about 75% of the sun's mass. The remaining 23% is mostly helium, the second lightest element. These two elements aren't just hanging out in the sun for fun, they're hard at work. In the hot, dense core of the sun, hydrogen atoms undergo a process called nuclear fusion, where they combine to form helium, releasing a tremendous amount of energy in the process. This energy then radiates outward, eventually reaching us as sunlight. But wait, there's more to the sun's elemental story. The remaining 2% of the sun's mass is made up of trace amounts of other elements. These include heavier elements like oxygen, carbon, neon, and iron, among others. Although they're in small quantities, these elements play a crucial role in shaping the sun's behavior and contributing to its various activities. For example, some of these elements are involved in the creation of sunspots and solar flares. Others affect the sun's luminosity, the total amount of energy it emits, which is a staggering 400 trillion watts. That's enough to power all of Earth's energy needs for millions of years. To put it simply, the sun is a celestial smorgasbord of elements, each playing their part in maintaining the sun's energy output and influencing its activities. It's a testament to the intricacy and complexity of our universe that even something as seemingly simple as a star can have such a diverse and crucial composition. Understanding the sun's composition is key to understanding its behavior. But there's one more piece to the puzzle: the sun's magnetic field. The sun's magnetic field is a crucial player in the cosmic drama. It's a force that shapes solar activity and influences Earth. This magnetic field is not a static entity but is continuously evolving, much like an artist continuously reworking a masterpiece. It's a product of the sun's inner workings. Specifically, generated by the convective dynamo action taking place in the sun's core. Now, what do we mean by convective dynamo action? Imagine a pot of water boiling on a stove. The heat from the stove causes the water at the bottom of the pot to rise to the top, where it cools and descends, only to be heated again. This is convection. Similarly, in the sun's core, the movement of hot, electrically charged gas or plasma generates a magnetic field. This is the dynamo action. But the sun's magnetic field isn't a simple, uniform field like the Earth's. It's complex and ever-changing. The sun's rotation combined with the plasma's convection twists and tangles the magnetic field. This creates areas of intense magnetic activity which we see as sunspots on the sun's surface. These sunspots are the birthplaces of solar flares and coronal mass ejections, dramatic events that can send waves of charged particles hurtling towards Earth. The sun's magnetic field doesn't just shape solar activity, it also influences our planet. It can interact with Earth's magnetosphere, triggering beautiful auroras and sometimes disrupting our technological systems. So understanding this magnetic field isn't just a scientific curiosity, it's a necessity for our modern world. So the sun's magnetic field, its structure and composition all play a part in shaping our planet's climate and technological systems. The sun is much more than just a bright light in the sky. It's a celestial dynamo composed primarily of hydrogen and helium with a smattering of other elements. This colossal energy source churns out an impressive 400 trillion watts of power, driving our Earth's climate and sustaining life. But there's more to the sun than meets the eye. It's a turbulent theater of solar activity, from sunspots to solar flares and coronal mass ejections. This activity is orchestrated by the sun's magnetic field, a product of convective dynamo action, which is in a state of constant evolution. The sun's magnetic field and solar activity can directly impact our planet. They can influence Earth's magnetosphere, trigger spectacular auroras, and cause space weather events that can disrupt our technology. Understanding the sun's structure, composition, and magnetic field is vital for predicting and mitigating these effects. Next time you glance up at the sun, remember it's not just a celestial body, it's a complex, dynamic system that directly influences our life on Earth.